Okay, let me start it. My name is Yuta Kasai from Nagoya University in Japan. Today, I'd like to talk about spatial skyline queries on team. Here is the outline of my presentation. First, introduction for skyline query, what team is, and our motivation. Then, I'll talk about our proposed methods. After that, I'll show you performance evaluation and how fast our proposed methods are. Finally, I'll tell you summary. First of all, let's consider the decision of the meeting place on the plane. There are several candidate points and several people standing on the plane, and we need to find a good place for all of them based on the distance. A spatial skyline query has been proposed to solve this problem. Let's look at the definition of a set of good place that is a spatial skyline. For a set of query points Q, we donate that PA precedes PB when the green candidate point PA dominates PB. For example, if we choose PA and PB in this figure, we compare distance from 3 people to PA and PB. PA is closer for all of them than PB, like this. It indicates that PA dominates PB. The spatial skyline is defined that a set of points that are not dominated by any other points by comparing the distance over and over again. There's no research that extends this to 3 dimensions, but let's try to define the spatial skyline in 3 dimensions. For example, in a mountain, there are several places to rest and stay and several climbers. When you want to gather everyone in one place, this question becomes how to decide where to go, like the meeting point I just said. Thus, we can solve these problems by calculating the Euclidean distance between 2 points over and over again as a spatial skyline query to find a good place. Existing studies like spatial skyline queries use the Euclidean distance between 2 points as the travel distance, but there is a problem with this distance. For example, when the yellow person go to a certain location, he or she naturally needs to walk on the surface of the train. On the other hand, the Euclidean distance between 2 points is a straight line, ignoring the train and solid objects. Of course, you can't move through the air. In other words, there's a problem that the error in distance between the actual surface distance and the Euclidean distance becomes large when moving through the air or through an object. In order to consider such a movement between 2 points more accurately, it's necessary to consider a 3D model in addition to positional information. Therefore, in my research, I will use data called team to solve problem. Next, what is team? Team is a network data that has surface information of the train represented by points in 3-dimensional space. Using the surface information, it's possible to calculate more accurate travel distance. However, the problem is the cost of calculating accurate travel distances. When the number of points representing a team is n, the cost of calculating the distance between 2 points is n squared times. Furthermore, if we directly apply the distance on team to the spatial skyline query, this calculation will be repeated thousands of times. We cannot get that wrong. In my research first, We propose a spatial skyline query based on the distance on tin in order to make more accurate distance-based queries. The contribution of my research is not only to make the query possible, but also to reduce the number of high-cost computations, since the query needs compute distance on tin over and over again. As a result, the proposed method reduces the number of heavy computation by 1% and the execution time by 1,000 times. I will explain how to solve spatial scaling queries on tin by comparing naive methods and our proposed methods. First of all, in the existing spatial skyline query, the distance is computed thousands of times in order to determine the dominance relation based on the candidate points and query points. On the other hand, in our proposed methods, before calculating dominance relation, we always prune the data points and that cannot be skyline point. After pruning data points, we calculate skyline points with simplified dominance check. It skips heavy computation in some cases. Even if the surface calculation on tin is necessary, we can also reduce the response time by filtering the tin already required for the calculation. Of course, we can get the same answer like naive method by adding 3 operations. I will explain them in order. The first step is simplified dominance check. In this step, we use Euclidean distance and network distance instead of comparing surface distance. This figure shows the network structure of tin. The calculation of the surface distance shown in yellow is high cost, so we want to make the calculation faster somehow. The existing research showed the upper and lower bounds of the surface distance in tin space. The lower bound is Euclidean distance, as I show green line. Next, noting that tin is a network set. The upper bounds of the upper bound is the network distance, as I show red line. Using this equation, we can rewrite the dominance check with the first equation in the definition, and finally get the second equation without the calculation of the surface distance, which allows to make the dominance check much faster. The surface distance part is now the network distance or Euclidean distance. First equation is always satisfied when the derived second equation is satisfied. We can use the Euclidean and network distance in constant time by doing a simple calculation in advance. So we can do dominance check quite fast because it doesn't need to compute high cost surface distance. Next, we will replace this dominance check with a geometrical problem. We aim to prove multiple data points at once with a certain rectangle and spatial index of dB. The most important thing of this topic, we can conclude gray points that are not included in the red rectangle cannot be skyline point. So we can prune these points without heavy computation. If we can prune many data points, the overall calculation time can be greatly improved. Combining the equation I said a diagram, we can create a green circles from the blue skyline points and the green query points. We can determine that a point is skyline point if it is included in one of circles, and also not skyline point if it is not included in any circles. In this example, the red point is not included in any circles, so it cannot be skyline point. Determining whether a point is included in each cycle is the same as the calculation time for the first equation. So we prepare the smallest rectangle that covers these cycles. If a point is not included in the rectangle, it's not included in any cycle. Whether a point is contained in a rectangle can be determined in a constant time. Therefore, we can reduce the number of data points faster than simply using the previous formula. After creating a rectangle, it's necessary to determine whether each data point is included in the rectangle one by one. We can skip scanning many data points from database by using the rectangle and the spatial index. Specifically, a spatial index such as an R tree is first created for data points. After the rectangle is created, we pass it to the DBMS to retrieve only the necessary points by using the index. When it works, we solve the Spatial Skyline query with much less data points. This is an extreme example, but even if you have teens and data points for all of your country, this operation allows you to efficiently retrieve only the necessary data points. Next, how do we select the blue points to create rectangle? Blue point is skyline point. We need to find at least one good skyline point somehow. If we created a small rectangle where we can reduce many data points at once, like this. However, when we select blue point to create a rectangle like this, it can't reduce any data points because all data points are contained in the rectangle like this. In fact, in order to create the smallest rectangle, we need to select the nearest neighbor to the green query point. When we search the nearest neighbor points on teens with a naive way, it is slow. But there's some researches on indexes to search the nearest neighbor points faster. We create the tight or loose surface indexes in the database, and they can retrieve the nearest neighbor points on teens based on a query. These two indexes are a set of boundaries, and they enable exact and fast responses to the surface nearest neighbor queries. The tight surface index on the left does not cover the entire team, but it's more tight. If a query point is within this boundary, the corresponding point within the boundary is the nearest neighbor point. For example, the nearest neighbor of yellow query point Q1 is blue P2. On the other hand, the root surface index on the right side is slightly loose and it covers the entire team. It has the advantage of reducing the number of candidate data points for nearest neighbor points. By constructing these indexes into a database with given data points, we can identify the nearest neighbor points without heavy computation. This allows us to create smallest rectangle out of all possible selections. Thus, we can prove many unnecessary data points. Finally, I will talk about removing unnecessary teens. We may still need to calculate the surface distance even if we do simplified dominance check and pruning data points. The algorithm to compute the surface distance on chin is not simple due to the nature of terrains, so we need to use all the given tin to compute it. However, the calculation time can be improved by cutting off unnecessary teens based on the network distance between 2 points, like this, because there are many teens that are not actually needed. Thus, we can point, we can compute the surface distance based on the minimum required teen, like this. That's our methods we proposed. We aimed to reduce the computation time by adding 3 methods in the spatial skyline on team. First, we created a rectangle based on the nearest neighbor to query points, and we combined it with the spatial index of the database to get only candidate points with possible solutions. Next, we determine whether the point is skyline point by simplified dominance check, which doesn't compute high cost surface distance. Finally, if we need to correct the surface distance, we can reduce the number of vertices in the team to reduce the computation time. Next, we evaluated how much each method contributes to speed up. We compared 6 methods: naive plus minimum bounding rectangle, naive plus rectangle plus team indexes, simplified dominance check, team vertex reduction, and a combination of all. The number of team vertices is 5,000. The number of data point is 100 randomly. The number of query point is 10. The range of query point is randomly within 2% of the area of a team. And we only changed one parameter in each evaluation. We measured the average time of 100 responses as a result. We generated team using the midpoint displacement method. It is used in the automatic map generation for computer games. This is a result of the change for increasing number of data points. I showed the number of calculation of the surface distance on the left and the execution time on the right, and the results are shown in a semi-log graph. First, we compare the naive one with the method with the minimum bounding rectangle. The naive one is blue and the rectangle is orange. As I mentioned earlier, when the rectangle is created randomly, the computation time does not change because we can't prove data points. On the other hand, when we use spatial index to find nearest neighbor in team to create minimum bounding rectangle, the result was improved. Let's look at the graph. The result is shown as gray triangle. The number of candidate points and the calculation has been reduced to 10%, and the response time has also been reduced to 10%. Next, let's look at the effect of simplified dominance check that we use Euclidean distance and network distance to avoid computing high-cost surface distance. It's shown in yellow. It turns out that when calculating the dominance relation, we actually only need to calculate surface distance in about 3% of the calculations, and simplification is applied in 97% of the cases. It means we don't have to compare surface distances in almost all cases, and we can compute its lower or upper bounds. Then we checked the effect of reducing the team. Since the number of calculation is the same, I only show the response time on the right side in light blue. There's no significant speed up in the response time compared to the other methods, but we are now able to perform the calculations in 80% of the time. Finally, we applied our method and showed the graph in green. By combining our methods, we have confirmed that the number of calculations of the surface distance was reduced to less than 1%, and the response time to less than 0.1%. This is the result we got from performance evaluation. I'd like to conclude by making the following points. In this study, we propose a spatial skyline query based on a more accurate travel distances on a team instead of Euclidean distance. While it is based on a more accurate distance, the calculation of team distance is heavy, and skyline queries involve such many heavy calculations, so we propose 3 methods to solve it faster. As a result, we confirmed that the problem can be solved fast. That's all. Thank you for listening.